Hi, in this video we are going to talk about mixed flow reactors of different sizes in series. I have already discussed about equal sized mixed flow reactors and equal sized plug flow reactors in some other videos. You can check those out. In this video we are going to talk about different sized mixed flow reactors. Now, for any known kinetics, uh, if we want to arrange mixed flow reactors of different sizes, then two types of design questions are generally asked. So, let me write down those design questions first. The first question is how to find the outlet conversion X from a mixed flow reactor system. And the second design question is how to find the best setup to achieve conversion X. Okay, so these are the two types of design problem questions that you can ask when you are designing mixed flow reactors of different sizes in a series condition, series configuration. So, while we address these questions, let us come to the first question. Okay, so how to find the outlet conversion X from an MFR system? So, let me just write this outlet conversion X from a mixed flow reactor system. This is our first target. So, for this purpose, we generally go to a graphical procedure. Okay, we use graphical procedure, and this graphical procedure was developed way back in the 1950s to find the outlet composition from a series of mixed flow reactors of different sizes. Okay, and the procedure that I am going to show you is applicable for negligible density change. So that is one of our assumptions. There is no there's no density change, so we can consider the volume ratio epsilon to be 0. Okay, uh, following on the lines of this graphical procedure that I will discuss, you can also derive the same method for systems with density changes involved, but as of now we are going to discuss for the simplest case, that is without any density change. Okay, so for this purpose of graphical procedure, we need the R versus C, that is reaction rate versus concentration curve for whichever component whose conversion you want to find out. Let me say that component is A. Okay, and once we have this data, all we need to do is plot it. But let me just show you how do we interpret the plot by writing down the design equations first. So previously when I have spoken about mixed flow reactors in my other videos, I have already written down the design equations. So design equations are like V by Fa naught equals to tau by Ca0. Here V is the volume of the reactor, Fa naught is the molar flow rate at initial state, that is for A. Tau is the space time, Ca0 is the initial concentration, equals to Xa by minus Ra. So Xa is the conversion and minus Ra is obviously the rate expression. Another way to write this is tau equals to Ca0 Xa by minus Ra, or you can also write Ca0 into Xa final minus Xa initial by minus Ra. Okay, so I for initial, F for final. All right. Now let's say you are going to uh, take into consideration one case study where we have unequal sized mixed flow reactors. Let me draw it out for you and write the notations. So this is one mixed flow reactor. From here we have in another mixed flow reactor. So this was the inlet point, and then we have another. So you can clearly understand that they are of different sizes. Okay, so initially at the first reactor, this is reactor 1, 2, 3. So at the first reactor, we have C0 concentration, V as the volumetric feed rate, in small v, if not as the molar flow rate. Okay, for this second reactor, we have C1, V, and F1. This is again equals to F0 C1 by C0. Okay, this is at the inlet point. Let me just write this at the inlet point. Okay, and for reactor 3, we have C3 V F3 equals to F0 C3 by C0. So this is for reactor 3's inlet, and for the outlet, okay, sorry, I made a mistake. I should have written here C2 because this is from the outlet of C2. C2, F2, and C2 by C0, and at the outlet, which is the final point from reactor 3, let me note that as C3 V F3 equals to F0 C3 by C0. Okay, so this is the convention that we are going to follow. Now let us write the design equation for the first reactor. Okay, so for reactor 1, you can write tau 1 equals to V1, whatever is the volume of the reactor, V1 by V, which is a volumetric feed rate, that is equals to C0 minus C1, because at the outlet of the first reactor we have a concentration of C1, divided by minus R1. Okay, this is the rate kinetics. Now if you take the reciprocal of this, then you can write minus 1 by tau 1 equals to minus R1 by C1 minus C0. I guess this is fairly simple. It's just a mathematical manipulation. Okay, so if we follow in these lines for the ith reactor, reactor I, you can simply write minus 1 by tau I equals to minus Ri by Ci minus Ci minus 1. This is the notation that you can follow. Okay, now we'll come to the graphical part. So this is how the design equations are written for each of the reactor. Now we will plot our rate versus concentration plot. Okay, on the x-axis we will have concentration C, and on the y-axis we have minus R. If you plot this, let's say you get an arbitrary curve like this. Okay, and this is your point C0, right? This is the point C0. When you come to the concentration C1, which will obviously be lower than C0, that is why I am moving in the negative direction of x-axis. So for C1 you have the corresponding rate. Let's say I am going to protrude this from x-axis, and I'm going to say this is the first rate. So this becomes the point where we see the C1 minus R1 point on the plot. Okay. Similarly, as you move for the second reactor's outlet C2 over here, and then let's say the corresponding rate is minus R2. So this is how you have got the points. Now if you draw a line between these 2 points, that is C0 or the initial concentration and the point on the rate curve that corresponds to C1 concentration, then this point, or rather I should say this line, is essentially minus R1 by C1 minus C0. How is that happening? Because if you see, this forms a right angle triangle, right? So this line is essentially the hypotenuse, and this is the perpendicular, and this is the base. So the perpendicular is obviously minus R1 magnitude, and the base is C1 minus C0. So we can easily write this. Okay, and this, if you correlate with your design equation, this is equals to minus 1 by tau 1. You can do the same thing when you go from C1 to C2, right? So this line slope will give you minus 1 by tau 2, and you can do this for I till the ith reactor. Okay, so this is how you find the conversion for your unequal size reactors, because once you know the space time, you can fit it on the design equations and get your desired quantity. These are the main design equations, right? So based on that, you can find the conversion. That is how you reach about the first design question for mixed flow reactors in series when they are of unequal sizes. That is, what is the outlet conversion X from a particular mixed flow reactor in the given system. To take up the next question, I'll meet you on another video. This is it. Thank you.